Okay, hello everybody. So we're back after a huge break, the Christmas break, and oh, how to get back? That's the tricky question. Okay, so the plan, we have some ambitious plan for today. I hope that we can finish the phenomenological part of this lecture today, and I think it's a reasonable ambition to have. So we previously were talking about interference mostly, right? Which allowed us to, like we say, the block of discussions about interference gave us some idea about the structure of the theory. And now I want to shift gears and leave the structure alone, and focus on dynamical part of the whole theory. So we will talk about a couple of experiments, couple of observations that will give us some clues about how things change in time in this theory we are probing here. So first, previously we were using coarse grain measurements all the time, and now I want to shift gears and let's talk about the opposite. So let us consider that we have access to perfectly fine-grained devices. That is, those are.
Do you mean continuous variables?
No. I mean that those devices are not coarse-grained version of any other device. Okay, but you cannot find any device that could be considered as a fine-grained version of those devices. And
what is the difference between continuous variables?
Not necessarily continuous. You can have spin, for example, which is not continuous, but you could not have a finer spin measurement.
We won't be getting into uncountably, where the measurement results are always at least countable, and ideally finite set of results. We don't want to go to the continuous variables and stuff like that, at least not for now. But we want to focus on perfectly fine-grained devices, and just to as a convention, I will use, so we have K, L, and so on. That would be to denote those observables that are perfectly fine-grained. And the letters we used previously, so F, G, and so on, would be used for some generic observables that could be coarse-grained, fine-grained, whatever.
You use Fortran notation.
Fortran? I don't know.
K, L, I, J are for integer variables.
Okay.
If you don't specify them, by definition, they will be integer. The data representation is integer.
It's like K, L, that's fine-grained.
N.
Okay. So I'm not comfortable with Fortran, so I will use my invention. Yeah, it's kind of like that. Okay, so these will be fine-grained, and those would be generic. So could be coarse, could be fine. We just don't specify. Okay? And we're already using FG, so you know. And now so there is just as a reminder, let's go back to the very first our first observations. We talked about causality, causal structures, where we found out that if you take a probability, let's use our fine-grained devices for now, that there is a causal structure for our measurements, for our probabilities, in the sense that you can write them as a product of conditional probabilities. Right, so you have, let's erase this. Okay, J conditioned by vector of tuple of previous guys, J conditioned by previous times, okay, J conditioned by previous results. Right, so we have product, and we have the first one. K1, T1, K1. Okay. So it's like it's the thing, the causality, right? So you have a first measurement, the second, and you can write your probability or joint probability, multi-time probability as a probability of getting some measurement at time T1, then times conditional probability of getting next result that is conditioned by the previous result, times conditional probability that's conditioned by two previous, and so on and so forth. So you can, the causality, the observation number one, causality that tested the structure was based on the, so we have the product here, but if you isolate the last one, Tn minus 1, the last factor from this product, then the rest of the factors you can just, that's joint probability with one less argument, right? Tn minus 1. Kn minus 1. Right, so this has to be a probability distribution. So that's why the observation number one, when we found out that when you marginalize over the last argument, right, you get the shorter joint probability. So that's why this observation number one tested this causal structure, as we discussed after some discussions. And now, bearing this in mind, we go to the our first observation of the day.
Observation of the day.
It's first. It's already special, but it's first of the day. But it's actually observation number 9, Markovianity. So now, its wording is very simple. The probability distribution describing measurements with perfectly fine-grained K devices with distribution describing measurements with perfectly fine-grained devices. So we have some collection of Kn, we have Kn device, K1 device, device. Right, so let's write it like this. Factorizes as follows. So we have this product here, right? And the later factors depend on everything, the more the dependence is getting deeper and deeper and deeper, right? When you go further in time. But if the devices deployed are perfectly fine-grained, it happens that this simplifies a bit. Kn. So you have product to n, and you have kj minus 1 without vector. Tj minus 1. kj minus 1. So these are just single, the latest guy. And times pk1 t k1, the first probability. So this is in a standard theory of probability, this property where you have this this causal structure is simplifies to this, like depending only on the previous, the latest previous outcome. It's called Markovianity.
So this is the definition of Markovianity.
Yes.
You didn't define it before.
Yes. This is this specific property
Defines.
is called Markovianity in a theory of probability. So we adopt the same name. This is Markovianity for us as well. And this is this name, this property has some, there is some baggage, historical baggage around it, because people often like pair it with a notion of memory. Say, oh, Markovianity means that there is no memory in the system, in the processing, whatever. And the justification for this, why it could be memoryless.
How do you define memory?
That's my exact point. So why people like to call it memory? Because this factorization implies that if you just take your some probability Kn Tn conditional probability like this, which is by bias rule, is a ratio of Kn Tn Kn divided by, right? This is by definition. And now you have this factorization, right? So you will write here K conditioned by Kn, T conditioned by Tn, Kn. Here you have product of going from 2 to n, Kj minus 1, Tj minus 1, J minus 1, and you divide this product See, so this just everything cancels, and you are left with right without vector. Well, I'm basically rewriting what I wrote above, right? So this, if you think about, I'm just saying that you take, if you think about, you have your conditional probability that depends on some sequence, past sequence of events, right? Okay, and you associate this with memory. Like, oh, so this random variable remembers the previous events, and this is what determines what it will do in the future. And when Markovianity tells you that this dependence is just, you only remember the last guy, not the previous guys. Okay, so it's like, oh, so it's.
I like this association because the only thing you did you replace the word depending on remember by remember. So this is the only difference, and there is something wrong in this formula.
No, the formula is correct.
Can you? I have to ask you. Look to the right hand side. In the denominator, you have P, K, T, blah, blah. And then, if you cancel this, there is some Tn minus 1 which appears there.
PM.
How come
Oh, no, sorry.
T disappeared?
No, sorry.
T disappeared somehow. And you didn't.
Too many ends. Sorry.
Okay.
This is what I meant. Okay. Sorry. Yeah.
You changed notation. You call this Tn plus 1.
Sorry. That was a mistake.
Okay, but coming back to this memory, if something depends on everything in the past, it is okay, you can say remembers what happened in the past, or it depends on what happened in the past.
Let me posit to you a scenario where the confusion might creep in. Because if you think about, okay, you have no memory, that it sounds like you are saying that your memory is short. Right? You have very short memory. You just remember the last thing that happened, right? But not the previous things. Right? So no memory is like very short memory, at least like intuitively, or if you just think about it.
Good, but short.
Good, but short, okay? But you see, but short memory would imply that there is some, when the time between this future t and the tn, the last event in the memory, it has to be, if it's long enough, then you forget. So you see, short memory would imply that there is some time scale, right? That you could disregard everything that happened before certain time, okay? But Markovianity doesn't care about how long ago the last guy was, okay? It could be 17 years ago.
You then, in order to criticize the memory, first you introduce new concept, short memory. So you said that there is some time which tells you how good, and then you criticize this time because it doesn't tell you about this time. This is not fair critique.
I'm not making this up because this is how people usually say it. So there is a lot of confusion. People, for example, think that Markovianity means that correlation time is short, for example.
Zero is short.
But that's not what it means. You can have Markovian process that has zero correlation time or infinite correlation time. There is no relation, okay? It doesn't matter.
Okay.
Correlation time.
If we didn't define correlation time, I know this.
Because but people correlation time associate. I saw it. This is very common. They associate it with like how long is your memory, and then Markovianity comes in, memorylessness. Okay, so it's short memory, and they say that okay, so your correlation functions have to be like deltas or something. So I just want to. I want to comment on this. Don't fall into this trap. Markovianity it's defined by this factorization, very specific factorization. And my advice would be to forget about memory, pun intended. Okay, don't replace Markovianity with saying that's memoryless. Okay, there are other things that are more, we'll get to this. Okay, so Markovianity, what physically Markovianity gives you.
I can imagine, just said, I can imagine that I can have a non-Markovian process with a short correlation time, but other way around, can I have a long time correlated process, as you said, Which is Markovian.
Yes, you can have infinitely long correlation time. Look, if you have like, I don't know, solution to Newtonian equation. So let's say planet revolving around sun.
Depends on the initial condition.
It is Markovian process and has infinite correlation time.
Okay. Because from step to step, it's.
Yeah, you
Okay.
see? You see?
How we define the correlation time?
Well, normally, you could take a position, for example. And because it's periodic, right? So it's a given position at any time, you can perfectly determine what would be position at some advanced time. So this means the correlation time is infinite, right?
If you have differential equations, everything depends on the initial.
So it's Markovianity is more about, it's a structure. No, it's not about structure. It's about like how the process, the sequence unfolds. Okay, the mechanics of it. Correlation.
But nevertheless, when
About-
we have the planet going around the sun, even if there is infinite correlation time, I think that the planet doesn't remember when it was. The only thing what is important is just when it.
I think planet.
So this is very.
I think planet does not remember anything because it doesn't have brain.
Question that you are asking, saying that the memory. I think that it has no memory, and no memory
Yes.
doesn't mean that there are no correlations.
No, that's see, that's not. That's why don't use memory. Okay, just don't use it because it's just confusing.
But I don't criticize it.
No, okay.
Only when people confuse this.
And that's why I'm criticizing, because this confusion it's everywhere. Okay, it's like.
No, but does it introduce something
Yeah, because
extra despite the confusion? It only introduces confusion.
Yeah, it's not very. The intuitions that come from using word memory are just lead you to dead ends, and you are making mistakes. And this is, I've seen it many times. Łukasz is always raging about it because he's promising that he will write this paper discussing this difference, publish it on archive some days to just show everyone that look, this is this distinction, don't confuse it. So that's why I'm commenting on this here. Okay, maybe it's unnecessary, but it's a pet peeve of mine. So I just commented on it, and it's really common mistake where people confuse correlation time with Markovianity, short correlation times. Okay, so what is the physical ramifications of correlation time?
but if there is very short, maybe there is such kind of or is it incorrect? If correlation time is short, it implies Markovianity.
No.
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 But the other way you explain, I can have.
There is no relation whatsoever.
No.
There is no. It's just not related. Markovianity is not related to correlation.
Give example of
Correlation. White noise, Gaussian white noise is a standard example.
Yeah.
It's a Markov process that has zero correlation time. You can take.
It is not Markovian.
It is Markov, and has zero correlation time. You can have non-Markovian white noise. I think you.
Let us stop at white.
Yeah. Okay. So and you can have Markovian process, Ornstein-Uhlenbeck process, for example, that has finite correlation time, or example with deterministic solution to equations of motion. So Markovian process that has infinite correlation time. So it's there is no relation whatsoever. Okay. So where Markovianity comes in? Okay. So now we touched upon it previously a little bit in the very beginning, and now is the moment we'll be coming back to this one matter. So you see, we are talking all the time about those probability distributions that were obtained from experiments, so on and so forth. But the description we're using so far, so you have probability, you have, so your collection of observables, right? This actually is not a complete characterization of what's going on, because what we are missing, the element we are missing here is the initialization, okay? Because, if you want to get those probabilities from experiments, right, you have to be able to compare past experiments with future experiments, right? So you have to have ability to initialize your experiment in some way, right? And those probabilities that you obtain will depend on this initialization. So in reality, we should rather use that this is probability like was before, but it depends on some initialization. Initialization event. Okay, and now what this initialization event is, you can imagine that it could be, in principle, it could be anything. I mean, there maybe we would be forced to actually introduce some categorically distinct devices that are responsible for initialization, something that is not measuring device, but its job is to initialize this the system into the state that we can then do our experiment and compare it with previous instances of experiment or future instances of experiment. And if this initialization was really something completely different than the measuring devices we are using so far, that would be very problematic. Because at this level that we are talking about here, any two measuring devices are already, could be very different from each other, right? And now that if we were forced to introduce another category of devices that is distinct from those measuring devices that are already distinct in between them, that would be like, probably we would hit a dead end or something like that, okay? But fortunately, Markovianity comes to the rescue, because Markovianity allows us to define initialization with measuring devices, okay? And why is that? Well, so Markovianity tells us that if you have probability that's conditioned by some fine-grained measurement at time t0, let's say, well, let's say 0 time. Some result k0, right? This conditional probability, because fine-grained measurement cuts off your memory, right? This probability is equals, if you had k0 and here was some f, g, whatever, tn0, some minuses 1, minuses 2. There's some past. Fn conditioned by k0, f minus 1, g minus 1, whatever. And it would be, and this would be the same if there was some different past. k0, and here's some f prime, g prime, whatever. Markovianity tells us that doing fine-grained measurement cuts off the past, okay? It doesn't matter everything that happened before this fine-grained measurement cannot affect what will happen in the future, okay? So this can serve as a proper initialization, because this is what we want from initialization, right? We want to reset everything. Don't worry about what events that happened previously, okay? So Markovianity gives us ability to define initialization, without which we wouldn't be able to formulate anything, I would say. And this has nothing, we are not using any fancy quantum mechanical properties. Okay, I would even hypothesize here that I think that every theory has to have this kind of Markovianity.
Unless you will tell that everything depends on the entire history.
Yes.
And this, so then you cannot predict, you cannot repeat experiments.
Yes.
Then
Yes.
you have a theory which you cannot verify because you cannot set the same initial condition. Then for each event you have to.
And this is even stronger because it's we are not forced to introduce some something else than measuring devices, which are already we are not very specific about them, what they are, but now we don't have to worry about introducing something that's even, it's not specified again, but different from measuring devices. Everything is in closed, logically closed. Okay, so this allows us to proceed anywhere. So what comes to my mind with this is like, I don't know if you read this science fiction book, Free Body Problem.
I heard about it. Yes.
Yeah, so there was some space aliens that had like almost magical powers, so advanced technology that it almost looked like magic, and they were infiltrating humans. Essentially they want to colonize Earth, and to do this, they interfered with. They wanted to stop the progress of science in humans, so they had to interfere with fundamental research on physics. So what humans observed was that they couldn't initialize their experiments. I mean, it depends on everything. They couldn't.
But this is a case of astronomy. You cannot reset the initial conditions. So
Yeah, that's why.
Yeah, that's a real problem.
That's why you
Cosmology
So
has
is
only
it
one
is it
universe.
yes. So this is a problem with cosmology for sure. But what they are doing, they replacing. It's like instead of initialization, you go for some not ergodicity, but that everything is uniform. Okay, so resetting is like looking at different, solid angle of sky or something like that. So it's like, so they are doing initialization by rebuilding the whole experimental setup.
Universal initial condition.
I mean, it's like because
one initial condition, but they can divide it in parts.
So it's like if you didn't have this notion of initialization through some applying device, then I guess the only thing that you would be left with is like, okay, so I'm just building identical perfect copies of my experimental setup.
But if you think that this is the only scientific point of view that everything has to, it means that such way of thinking does not apply to many or most of the things that we have in life. You cannot reset yourself. So biology is part of scientific
yes. So
insight. According to you, that you only have to have such device which
physical theory.
Physical, okay, physical. So it shows that physics is extremely limited to something that you can
I'm
initialize only and start with to do.
I mean, with life, you can.
So it does not apply.
Resetting is like building copies of organism, right? They are not identical. We know they are not identical, but there are enough similarity that you can, each instance of a member of a herd, you can like count as a new experiment, as new initialization, I guess. And same astronomers do the same thing, right? They assume that looking at different solid angles of sky is like taking another copy of the fragment of the universe. If they didn't assume that, there is no astronomy. But if you are thinking about physical theories, I mean, the historical precedent show us that we can be greedy, because physics seems to describe some like fundamental laws, right? It's on a fundamental level, right? So that's why we can be a little bit more greedy, or try to be a little bit greedy. So if you want to have a theory that describes something on fundamental level, then I think this Markovianity, that's something that allows you to initialize with same kind of category of devices as you do measurements, it's necessary for this theory to have the form that we are like used to. So that's so Markovianity for me is not, forget about memory again. Markovianity is about this ability to initialize. Markovianity means that it's initializable. Okay, that the thing described by your probabilities is initializable, can be initialized. So this is, I think, less confusing and more to the point, what it means. So one more thing here. If we have this ability with initialize, and this is important, that the initialization has to be done with fine-grained measurement, okay? Because only for them you have Markovianity. And by the way, this gives you kind of a phenomenological criteria for determining if your devices are truly fine-grained, right? You do the sequential measurement and look for factorization. If they factorize, then okay, so they are fine-grained. If they don't factorize, okay, so there is some coarse graining involved. So this is important, okay? That it has to be like ultimate precision of device, I guess. Once we have this ability to initialize with application of device, we can build on it and introduce some, let's say, uncertainty on top of that. If you want to have more fancy ways to initialize, you can always like add some probability distribution for, okay, there's some probability that was initialized with this measurement, and some probability that was initialized with some different measurement, and so on and so forth. Yeah, I mean, yeah. If you now remember standard quantum mechanics, this is where mixed states comes from, right?
They can be defined.
Yes, exactly. So you can have initialization that's let's write it like this at time 0, Fn, and conditioned by some distribution small p. Okay, this will be a probability distribution, and by definition this would be just so we take Fn conditioned by k0, Fn vector. So these things we know. This is initialization with a measurement, fine-grained measurement. And here we have our distribution that values and devices, right? And you just have to sum over everything. About k0 and sum over small k0 that's in a spectrum of given k0 device. So you can like have more fancy initialization, which can mean, like with probability distribution, it can be used to parameterize, different things, ignorance, randomness, some other, whatever you wish. But this is a proper probability distribution that we wrote here, okay? And yes, so Markovianity, and it's again, I think I would say that this like causality, this didn't have nothing special about quantum mechanics here. Okay, this is just I think that all physical theories would display something like this. Okay. So we're just checking that quantum mechanics is not aberrant in this sense. Okay. All right. So I propose to make a 5 minutes break, and then we go to last two things, and we will finish the phenomenological layer. And then next week we will start to deduce the formalism. Okay. So let's go to the second part. So yeah, so we have Markovianity, we have initialization. Good. Now we go to the next part, quantum Zeno effect, as you can see on the title. So we are still talking about fine-grained measurements. Okay. And now imagine the following scenario where you're doing your fine-grained measurements, but you're doing your measurement, maybe the one that prepares initialize, and then you do the other measurement, but it's like immediately after the first one. Okay, so you do one, and immediately immediately after that you do the other one. Rapid measurements. Intuitively, right? We would expect that if you leave no delay between those two measurements, they both should give you the same result, right?
If dynamics is not very fast.
I mean, you are doing it so fast, it's faster
It's faster than everything.
Yeah, if it's super fast, we expect to see that there's nothing changes, right? And this is actually what you observe. So
If you observe a snake.
Yeah, like Zeno did, right?
You're so here you expect that minutes later it will be also there.
So let me write it like this. Okay, given k0, and let's take limit delta t goes to 0. Okay, and what we expect and what is actually seen, you would see data k0. Okay, so that's cool. This is good. This is what we expect. But this our expectation is of course built on our classical intuitions, right?
Yeah. Why we expect it to be continuous that much that
because our brains work in a trajectory picture, right? If observables are represented by trajectories that are continuous, right? Because like some violent jumps would be hard to imagine, would be some weird dynamics would have to happen, right? So if they are continuous, so if you would just do one measurement,
unless you live on the stroboscopic line, then you don't see continuous evolution. Yes.
Yeah, but then.
But if you don't go to such places where they have the light, you see that continuous movement.
Yeah,
I think it's our.
But still, you know.
It's surprising.
But what I'm trying to get here is that this is intuition built on our understanding of trajectory picture, right? So of course, you would expect that this, because the theory we are investigating, quantum theory, the trajectory picture is invalid.
Trajectory picture is we are used to because we use differential equations to describe classical.
Oh, that's
which are typically require that the trajectory is differentiable.
I mean, that's
yes.
Single. Look.
It's anyway a differential picture.
We can expect. I mean, we can anticipate that this intuition, our intuitive understanding, would be somehow subverted when you go to sequence of rapid measurements, right? Because this is what we learn. The one measurement, it's kind of classical, but if you do sequence, you can have some interference and stuff like that. Very non-classical behaviors. So and this is the contents of experiments on quantum Zeno effect exactly. This is where you apply your measurements, but you make it denser and denser and denser, right? More and more measurements, very rapid measurements, right? And then what will classically you would just expect to trace the trajectory, right? But quantum gives you something different. So let me write down the next phenomenological pheno-obs. This is number 10, quantum Zeno effect. Quantum Zeno effect. And it goes like this. Given perfectly fine-grained K device and a duration T. So they give us some duration, right? Some interval of time. One observes the following thing. I mean, the thing that can be quantified in the following way. So you take probability. When you do measurements with your device, you initialize with device K as well. And you have here Sn, initialize in term 0. You take limits, n goes to infinity. And you have K0, 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 which, since we are doing measurements with fine-grained devices, we have Markovianity, so we can rewrite it into the factorized form. Lim n goes to infinity. Now product J. I will define all the variables in a second. Let's write it like Sj plus Tn conditioned time Sj Kk, okay, K0, K0. And this, the limit is 1, where Sj, sorry, Sj is J times T over N. So what it means? So we take our interval and we plug in n measurements equidistant at equidistant intervals. So every T over N, we apply our measuring device, right? And we go to the limits where the frequency of those applications goes to infinity, right? So we have infinitely many measurements at this in this interval of time, okay? And what this inscription, this equation tells us that the probability of measuring something else in this sequence than the initial K0 goes to 0.
Can you give an example of such observation?
I mean, it's famous quantum Zeno effect.
Never saw that the atom stays forever in excited state.
I mean, Zeno experimental. People did some experiments to demonstrate quantum Zeno,
but not infinite.
Yeah, of course. I mean, this is, you know.
So this is some kind rather of.
This is of course this is idealization.
Observation.
N to infinity is idealization, but for large N.
Measurement is different, needs different, still. 중에 G spin direction and X direction. You are taking same measurement,
Yeah.
same measurement.
The same.
You're doing same device, and the probability of measuring.
You spin up or atom excited, then you measure spin ups, and you start to repeat it with the same device. So you measure the projection of the spin, you will see it always up.
So in other words, the probability that you measure in all results with the spin up is 1, goes to 1, right? Or in other words, the probability that
more dense for frequent measurement.
yeah, or the probability that you will measure spin down in the sequence somewhere goes to 0. Okay. So it's like the results you are obtaining from measurements become frozen. Okay. They are frozen to the initial.
First measurement is true.
First
Measurement will project it on spin 1, whatever it is.
Project.
Set 1. So it projects it on up. This is the initial data.
Yeah.
Just before that, it was
Before you don't know, you have 0 time. At 0 time, you do first measurement. You see it up. And then you repeat it immediately. And then you see it up.
I mean, this is not even, you don't have to take the limit. If you keep measuring same action direction and same.
No, it's not the same.
You
It's
need-
the same device. Device can give outcome up or down. But you measure it up.
If you
And then
take
you repeat it immediately, the evolution is frozen. And that is practically so. There is no time for speed, because if you make this delta T large, you will see some evolution, and then if you apply this Stern-Gerlach, you will see it either up or down. But
So
he says that
the-
when you repeat it immediately, you will see it up. So it means that there is no time for any evolution.
So if you take your time t, right? It's a fixed interval of time. You do your initialization, which gives you some k0 result, spin up, let's say, and you do second only one measurement at t, right? There is some probability that you will measure spin up again, right? But there is also non-zero probability that you will measure spin down, because there was some evolution from the beginning to end. But
And
now,
don't change the spin Z to sequence spin X. You don't.
You have
no.
Hamiltonian.
I mean, measurement device.
No.
Try to do it.
Experiment on Zeno effects assumes that you are doing the same measurements. Okay. If you do different, that's different experiment. Okay. If you would start mixed devices, would be different. That's different experiment. We want to focus on particular Zeno effect. Okay. So this is famous Zeno effect. Okay, you can word it like this, but it's since we can pair it with with Markovianity and essentially express everything from those conditional probabilities here. Okay, the fact that this limit gives us one identity gives us a lot of information about short time behavior, okay, of these guys, of this survival probability, as it's called in the business, okay. Because to obtain this limit, this PKK has to have the following short time behavior. Quantum Zeno effect implies, so you take PKK, take T plus delta T, okay, K0, and assuming delta T is small, it has to be 1 minus some coefficient V, depends on K0, depends on T squared, so it's positive. So it's a minus positive coefficient times, and this is important, quadratic term in delta T, not linear, quadratic is the first, plus something that's, higher order terms. this is what Zeno effect tells us, that you don't have linear term. Okay, why you don't have linear term? Because if you did have linear term, if linear term was non-zero, then you would get the following thing. So you take your product, this one, PKK Sj plus T divided by Sj, K0, okay. So this is the, so this is this thing here, right? If the linear term existed, was non-zero, you would have this 1 plus linear term, which let's call it capital L. So it's a capital L like Lagrangian.
Oh.
That's something that's n over 2, okay. And now when you go to the limit, if you know your analysis, you would get exponent integral from 0 to t L K0 S ts, which is, it's typically non-zero. So since we have Zeno effect, this limit is 1, we cannot have linear term. So it has to start from quadratic term. And this is a big input for us, because it tells us a lot about dynamics. This will be our, we will do a lot with this piece of information. And another interesting observation here, it's from Davide, one of my collaborators on this project. It's also very interesting to note that Zeno effect is quintessentially quantum effect, in the sense that if you have classical theory, so theory for which you have consistency, Kolmogorov consistency, right? So your joint probabilities, when you marginalize, you write the shorthand. If this is true, right, then you take some classical probability, Kn. So consistency tells you that if I marginalize this, I will get something shorted, but it also works the other way around. I can just insert however many additional arguments I want in between by, adding some sum. So if I sum over, what are my notation? I add some over kappa, classical Tn, blah, blah, blah. And at some place there is, I insert additional time point. How do I call it? S T1, is the kappa, and I can add another one. I can make it as dense as I wish. If I can do that, then everything would be frozen. Everything would be Zeno effect. So classical physics cannot have. There has to be this linear term in classical physics, this L, which looks like Lagrangian, which when you integrate is like action and stuff like that. So this is quintessentially, if your theory is inconsistent, it can and must, we will get to why it must, but it must exhibit Zeno effect. If it's consistent, it's classical, it cannot exhibit Zeno effect unless the observable is just, there is no dynamics, right? Because this is the only case when it's really frozen, when it's frozen. So so this is like interesting.
Yeah, there's no reason that there is no linear term. It's not due to the unitary quantum mechanics, or just simply without unity, you just get this.
We will get there. We'll get there. It's a
The unitary case, you automatically cancel because it's scalable, the entity.
it's not unitary. Okay, let's remember standard quantum mechanics. So unitary evolution operators have linear terms. Okay.
But this is for amplitude, not for probability.
Yeah.
Square it.
If you take square, you can get the problem.
Yes.
Yeah. So this is because essentially, because you have pairwise unitary evolution operator on its own has linear terms, but they come in pairs. Okay, this is like, we will get to this. I don't want to spoil everything right now. We'll get to this. But this is like indication. This is all connected. You know, the fact that you have inconsistency, the fact that you have interference, it's all related and probably equivalent. Okay, Zeno effect is everything's equivalent, and we will get there. Okay, and that was Zeno effect. So gave us a glimpse into short time behavior, which will, you know, this is a universal observation. Okay,
I think it is universal observation that patient theory is only take delta t squared the first step.
I mean, because but you know, before we get to Hamiltonians and perturbation theory on them, the easiest way to get to this is through famous Zeno effect. I was very proud when I figured out that this is like, I can cram in Zeno effect here to get real good, because you know, you could.
However, this has nothing to do with, I don't know, this interpretation of whatever this trajectory is, whatever.
No, it has everything to do with that. Actually, we'll
You can get the same. You need two permanent measurements, so it is standard formulation of with using states also gives the same.
but here you need more. This is a sequential measurement.
But people then repeat, okay, and then you have collapse, and then you repeat measurement. You have, and then it is
Okay,
just
standard explanation for Zeno effect is through collapse,
Yeah.
that you are collapsing state,
Yeah.
and this is incorrect explanation. We will spoilers, but we will explain it through interference effects, which is true. And it's actually this particular interference. It has to be like this, or everything else would fall. I mean, there is no other choice. It has to be like that. The interference has to work like that in this scenario. It's like, it's all connected. An explanation through collapse is just unnecessary. Okay? It's the same interference effects as we saw previously. It's interference between two trajectories. Okay, I'm going into spoilers now. Let's be patient. Next week we will have B trajectories. Now let's just collect our data, our inputs. There's one more input left, which will be easily fit in our remaining 30 minutes. So that's Zeno effect. We probed a little bit of dynamics. Not enough, almost enough. Maybe green now. So the next and the last of phenomenology subsection, 4.6. It's entitled multiple observables and uncertainty relations. Relations. Let's give it a underline. Boop. Okay, so the topic of multiple observables, how quantum it is, we already talked about it quite a bit. But let's but there is a I want to talk about like a more quantitative take on it. Okay, so in like I said it multiple times already, in classical consistent theories, you have only, there's this elementary observable. Okay, there's only one elementary observable. Every other observable is some function of this elementary observable. Okay, and if so, you can figure out what is the analog of perfectly fine-grained classical observable, right? So if we denote in classical physics, in classical theories, theories. So we have, let's say, E will be our elementary observable, which would be, we can represent it by some trajectories, some function of t. Okay, and for simplicity, let's assume it's a discrete. It has discrete values. Classical speed, like something that you telegraph noise could be modeled with. It has two values. Bit, classical bit.
Q bit or
Not Q.
fair bit?
C bit, classical bit.
Have you heard about fair bits? Fair bits. Fair bits? Very many bits.
So you remember, in general, this elementary observable, it's a vector, it could be real value, it's everything, right? But for simplicity, let's say it's just one single dimensional discrete value. So it's the closest to what we are talking about here. So if you want perfectly fine-grained observable, some classical K, which would be, how do I denote it? So this classical K again could be represented by trajectories, some K of t, okay, which, because it's classical theory, it is some function of is classical fine-grained observable. We want to make a model of E is the elementary observable, so the one, and the other would be a function. Okay, but we want to have a notion of fine grain. Of fine graining would be, you can go only as fine as elementary, of course, because it's elementary. So you would have your observation K would be some function of E, okay, and it's fine grain if this capital K function is bijection, how do you say? Bijection, one-to-one function. So you can always, for every value you have a inverse, right? So K that goes from omega E plus to omega K plus bijection, right? Then it's perfectly fine-grained, right? But what it means that any measurement of this K according to our stuff we talked about previously about trajectory picture of classical theories. So you would have here some filters, classical, which could depend on time if you really want it. A depends on the elementary trajectory, which has the master distribution, right? So in this case of fine-grained guy, this simplifies. So you have deltas E, no, sorry, K, Kj, capital K E at Tj. Simplifies like this. Which then again simplifies to because we have like only the finite number of discrete grid of times, right? So we don't need to use this. We can switch to multi-time distributions. This is what I want to say, which would be as k to -1 because bijection, so it's well defined. Kn, K1. Okay, so what it means in a maybe over formalized way, but what it means is just there is very little incentive of talking about different observables in classical theories because the measurement of any observable is essentially the same as measuring this elementary observable through, and this shows that, right? You're measuring K, but we're actually measuring E. Okay. So this can be like, that's my invention. You can summarize this property with what I call certainty relations.
Oh. Yeah.
Certainty relations.
Everything is uncertain, and you should use an uncertainty relation. Just use the certainty relation and
Yeah.
just few of them.
Yes.
Then say surely. Yeah, sure.
Surety.
Surety. What about if I have this classical, say, E, which is jumping on discrete grid in some parabolic potential and the energy is x squared? This is not bijection.
But then it's not fine-grained observable, it's coarse-grained.
Why? I have discrete point that the B can jump only by this distance, this way and this way.
Yeah.
And my observable that would be x discrete.
Okay.
It's x squared. It's x squared.
Observable is x squared. So it's coarse-grained.
This k is x squared. Its function.
Okay, so it's if your elementary would be x,
yes,
k would be x squared, so it's not fine-grained. K is coarse-grained because it's it has degeneracy. Yeah, exactly. So the certainty relations, let's write it like this. So you have delta E0, surety relations, and it's like on one hand, I mean, it's a series of equations. So this delta could come from taking the rapid measurements of our observable E, elementary observable, could come from this. This is delta. But because measuring coarse-grained observables is the same as measuring fine-grained observables is the same as measuring E itself, so equally well, you could obtain it as rapid measurement of, say, K, classical, KK, capital KE, capital K E0, or if K is one fine-grained observable, you could take another one, L, let's say, some different observable, but still fine-grained. class L class. So there will be some bijection L 0. But again, this is each fine-grained measurement is the same as measuring E itself. So you could obtain the same from doing K classical, L classical, K E, L E0, and vice versa. So those are certainty relations. Everything is certain because everything is not conditioned by caused by elementary observable, because this is classical theory, because there's trajectory picture. So this is the reason. And of course, if you have theory that is inconsistent, doesn't have trajectory picture, you are not necessarily constrained by certainty relations. You can violate them. You can have inequivalent observables, and you already seen this with coarse-grained, quantum coarse-grained observables, right? But you can also consider perfectly fine-grained observables, quantum observables that are different devices, but still perfectly fine-grained, both of them. And this gives us this is my version of uncertainty relations. Okay. Usually it's like I don't know what is the most common.
In a very fancy way, you wrote something that if you have bijection, so if you have y, x.
Yeah.
Because it's one-to-one correspondence. If you have another function and you have.
But I wanted. But I wanted to have the contrast to, that this is classical.
Everything is that you have only one elementary whatever variable.
Yeah.
So if you have any function of this variable, you know the value of the value.
Yes, and that's why you can you can talk about this elementary.
Doesn't matter what function you have.
It's
important that if you know the value of the function, you know the.
But that's why you can sometimes.
I like the sophisticated way you wrote.
Because this is
because you want to have analogy with quantum.
Also, but this is also the reason why you can have in classical theories the state of the system. You can just say this elementary trajectory is the state, because it gives you everything, because it's classical theory with trajectory picture working. This is like the reasons, right? So structurally, fundamentally, it comes from being a single trajectory theory, uncertainty relations. Okay, and it's worded like it's very simple. We're almost done. Given a pair of perfectly fine-grained devices, given a pair of perfectly fine-grained devices. So let's take K and L device as per our notation. One observes the following relation when the two devices are deployed in a rapid succession. So, this one after another is also a very useful tool. And the relations, of course, we take limit delta t goes to 0. You have p. You take k, l. So these are quantum of observables conditioned by t, some k, some l equals when you do it other way around. So we initialize with k, measure l. Okay, this is L. And I will denote this because it doesn't matter if K or L. I will denote this inscription as CKL for posteriori as this matrix element. Okay. But key thing for any T. Okay. This is independent of T. You do two rapid measurements at some time t, but this C, this correlator, is independent of specific time where you applied it.
It is symmetric.
And it's symmetric. And this also tells us something about dynamics. And we can add here another clarifying sentence where for any t, where CKK, KK prime is delta when L equals K, right? So this is the, two rapid measurements, but of the same observable you expect have two identical results, and this is, we confirm that this is the case. But in general, CKL, KL, it's not some kind of delta, okay? In general, it's not certainty relations. So in other words, quantum observables can violate certainty relations, okay? And there is a second part of this observation, which is moreover, for every fine-grained K device, it is always possible to find a perfectly fine-grained K perpendicular device such that CKK perpendicular KK prime equals 1 over omega of K for every K and K prime. Okay, so it's constant, independent what you do. So this is the observation. It's mutually unbiased basis, MUB measurements. This is what reflects from standard quantum mechanics. So since this matrix C is independent of time, you can think of it as a way to quantify how similar observables are, quantum observables, right? How similar they are. And you have on one extreme when it's...
I don't remember, omega of K was spectrum.
Yeah, then...
And what is modulus of
It's a size of the set. Power of the
What
size.
is size? When I have
Power was the
values,
number of the
You have discrete.
1/5. Then if I have five values, you will say.
Yeah, so you have spin, so two values will be 1/2.
1/2.
It's like, equally, there is no correlation at all, right? Everything is equally probable. So this C can be used as a thing to quantify how similar observables are. So on the one end, if CKL is delta-like, well, is delta, then it means that K and L are equivalent, like in classical physics. So essentially, K and L is the same observable. And on the other end, on the other extreme, you have this 1/omega, which means that there is no correlation whatsoever between measurements of K and L. They are like, in some sense, they are completely opposite. I don't know how to call it. They're orthogonal to each other. Orthogonal to each other, let's say. And and there can be many K. It's not like unique. K perpendicular is not unique, by the way, as it turns out. And it's, as a matter of fact, from standard quantum mechanics, it's unknown how many those perpendicular guys are for given observable. But it's and again.
No, here I am a bit lost. Of course, it's important. Now I see that it is important not delta. It's not changing the time sequence of two measurements gives different results. Because when I'm thinking about spin and I measure first X component and then Y component, or do it the other way around, I have different results. Yes.
If with spin measurements, you Z, let's say, sigma X, then sigma Z, you get 1/2, because they are, sigma X is orthogonal.
But you say the probability of getting some spin up and then getting spin in the perpendicular direction is the same when I do it in the opposite direction.
Yes, also. And it's independent on. Yeah, if you take sigma X and sigma, it doesn't matter what the actual values are. It's this correlator is one.
The level of probability is
no, it's not quantitative. I don't. This it's unknown. This is like mutually unbiased measurements. And it's like there is some theory about this. I read a bit about it, but it's not even known how many those K perpendicular are for given K. I think for qubits it's actually known. You can calculate this from some theorem to get it. But how it is related to commutator, I don't know. But this is like, it shows. And again, this is completely unintuitive to us, okay? Because this not only it shows that there are inequivalent observables, but that they can be like completely orthogonal to each other. This is just we just don't have any circuits in our brains to handle this, okay?
But this orthogonality does not correspond to conjugated the variables which are conjugated and they don't compute.
I don't know.
Like position and momentum.
I don't know. I'm not sure. I mean, we won't be using that too much. It's just a fun fact at this point. But it's this existence of K perpendicular is just to show that how non-classical we are. It's just completely unfathomable. I mean, you cannot fathom it in classical theory.
When you measure position, you have no information about momentum, so it looks to me like these are just not.
I think they are.
There must be some relation to the
Probably yes, but what is this relation? I don't know. But it's for sure position and momentum quantum mechanically are mutually measurements of position and momentum are mutually unbiased basis. Okay, so it would give you this. Of course, it's not a discrete value, but continuous value.
It's not like
So you know, but it's in this vein. Okay, something like that.
about say on the lattice, position on the lattice, and then also.
Yeah, but that's we are jumping much for because So again, this is very non-classical. So also unintuitive, but underlines the fact that you have quantum mechanics have many inequivalent observables. And for us, technically, we will be using the fact that it's time independent. Okay, in the second part of the lecture, which we finished the first part now. Okay, this is all the phenomenology we need. This is all the inputs we need. And next week we will start to collate it and deduce from it what is the formalism then that would be that is insinuated by all these observations, and hopefully it will be fun.
You will find Schrödinger.
No, I despise Schrödinger equation, because Schrödinger equation is the same as saying that you have unitary generated by some Hermitian operator. I prefer this.
Yeah, but at some moment you will have to introduce this psi or rho.
Yeah, you will see. You will see. You will see.
Also, evolution is not unitary evolution operator is you have to apply it to something.
Exactly. This is the okay where it applies.
Yeah.
And this we will deduce everything. Okay, this is enough information for us to do it. All right. So that's it for this week, and hopefully you will be here next week for the if you're alive still. Yeah. Okay. So.